In this video, I'd like to show you the basics of how to incorporate a PCB chip antenna into your own hardware design. The board you're seeing here is a 2.4 GHz RF dongle PCB incorporating a Texas Instruments CC2500 connected via SPI to an FTDI SPI to USB converter, which we can connect via USB Type-C connector to a host computer. And on the right-hand side, we can see the PCB chip antenna, which will be the focus of this video. The reason I went for a PCB chip antenna in this design is because of the rather small size of this board. Despite PCB chip antennas having various downsides such as lower efficiency, sensitivity to placement and routing, and so on, but we'll cover this more in detail in this video. I could have, of course, gone with a PCB trace antenna or an antenna connector, as well as an external antenna, but again, the reasons are I wanted to keep this module self-contained and rather small, and the efficiency decrease for my purposes was sufficient. This RF dongle PCB will then communicate via data link to my micro quadcopter control PCB, which has been featured a couple times on this channel before. Please do keep in mind, I am in no way an RF expert, and I'm just outlining tips that have worked for me in the past when incorporating PCB chip antennas. A huge thank you to PCBWay for sponsoring this video. I had these RF dongle PCBs as well as these micro quadcopter control PCBs manufactured and assembled by them, and they did a fantastic job. For this, I used their PCB prototype service as well as their PCB assembly service, and I'd strongly suggest you check them out. Links will be in the description box below. Make sure also to follow PCBWay on Instagram. Again, links will be in the description box below. As you can see, all the cool designs they're producing and manufacturing, and occasionally you'll see some of my designs pop up there as well. As stated in the beginning of the video, there are many different types of antennas we could go with when we're designing hardware. For example, in a previous video, which is video number 90 on my channel, we went through a complete ESP32 and PCB antenna hardware design. Here you can see these trace antennas, which are effectively antennas where the features are etched into the copper of the PCB. As you can imagine, this is pretty cost effective because we don't actually need an additional part which doesn't have to be assembled or bought, but there are other issues with this type of antenna. Many of these antennas are openly available, at least the dimensions, but there are quite a few issues with these. Another option is, of course, to simply use an antenna connector and then have an external antenna, for example, mounted to your enclosure, such as these antennas here, depending on what frequency, various other parameters, and what application you require. All in all, antennas are, of course, a huge topic, very, very complex, especially if you're trying to design your own antennas. Oftentimes, the software can be quite prohibitive. I'll leave many links and articles in the description box below for further reading, as this isn't intended to be an all-encompassing video, but I'd first of all like to show you some examples of why you might use a ceramic chip antenna, which we're doing in this video, versus, for example, using a PCB trace antenna, which was from video number 90. This article by Juni Lifländer, I don't know if I'm pronouncing this correctly, is quite good because it outlines some of the main features between these two types of antennas. Trace antennas, of course, manufacturing costs are pretty low because we're just simply printing this trace antenna or etching it into the copper features on the PCB, and we don't have to assemble a part. Oftentimes, these antennas are openly available. We can copy those reference designs, and if they're designed correctly, these antennas have a fairly reasonable bandwidth, and they aren't too large, of course, depending on the frequency and thus the wavelength of interest. The problems of these trace antennas, however, are quite important to know, especially if you're simply just copying a design. Objects close to the PCB antenna can distort, so to speak, the frequency response or the response of the antenna. They might have to be tuned. They're prone, of course, to manufacturing tolerances and by the PCB design as well. So you simply just can't take over a trace antenna you found somewhere and then copy it on your own PCB design. You will most likely need further tuning. And this can be, of course, quite difficult if you don't have the correct equipment. Also, these trace antennas, compared to, for example, a ceramic chip antenna, are typically for the same wavelength, same frequency, quite a bit larger than a ceramic chip antenna. On the other hand, looking at these ceramic chip antennas, of course, we have one point is cost, and we'll look at how much these actually cost. We'll go into a typical distributor, and of course, the cost to assemble them. They are an additional item on your bill of materials. They are, however, quite small. We have a variety of different configurations depending on your needs. We can choose different gains, different center frequencies, different bandwidths, and so on. And also, they aren't as severely detuned by close proximity to other components, and so on. But there's, of course, far more to this, and I'll leave some links in the description box below. What you should always consider, especially when designing a commercial product that'll be for sale, is always try to aim, unless you have a specific reason not to go with a pre-certified module, which typically integrates an antenna, always pre-certified with a selected range of antennas or types of antennas with certain properties. I'll leave some links again in the description box below to show you how it can impact the cost of your design, certification, length of certification, and of course how many obstacles there are in the way to get your module certified if you are incorporating your own PCB trace antenna or chip antenna and not using a pre-certified module. Just a quick Google search, there are very many pre-certified Bluetooth, pre-certified Wi-Fi, and different pre-certified RF modules available on the market depending on your specific needs. They use different microcontrollers, system on chips, and so on. So make sure to check out those options first if they fit for your design before trying to incorporate custom antennas, before trying to do this yourself, because the costs for certification and also the obstacles for certification are much, much higher if you don't use one of these modules. With that being said, let's continue on with seeing how you would go about adding a chip antenna into your own design. I won't be going over the details of how a chip antenna works. There's plenty of information on the internet and in books, of course, and I'll leave some links in the description box as usual. Chip antennas, as you've probably already seen, come in very many different flavors, sizes, gains, parameters, and so on, depending on the specific application you need, depending on if it's Bluetooth, if it's GNSS, and so on. For example, this is a demo board that contains various different chip antennas, be this for Wi-Fi, Bluetooth, GPS, and so on, and you can see the scale on the left-hand side. So these are typically rather small devices. For example, top left or bottom right, you can see they are very, very small devices, depending on the wavelength, depending on the frequency of interest, but they can get more sizable if we go down in frequency, that is up in wavelength. The question then is, for our specific application, let's say we want to use Bluetooth or Wi-Fi, how do we go about choosing a suitable chip antenna? Again, there's many ways of going through this. I can highly recommend this website, Johansson Technology, who happen to also manufacture antennas, and they have a cool chip antenna selection guide, where you might start on the left-hand side if you want to go with Bluetooth or Wi-Fi, which then determines effectively our center frequency as well as the bandwidth we require. So if we go with Bluetooth, we would be around 2.4 gigahertz as our center frequency. What we have to choose next is how our chip antenna is mounted. You can see we have end mount or corner mount, we have center edge mount, circular mount. We can see some examples of how these chip antennas might be mounted here. So top left, we might have a corner mount chip antenna, or on the board, you can see I have a center mount chip antenna. So there's different types depending on where on your PCB you will mount your antenna. And this might be due to space constraints, due to mechanical constraints, and so on. Once you have selected one of these, you can choose the size of the antenna. Of course, depending on the size, you might get better efficiencies, different radiation patterns, and so on. And each manufacturer should have somewhat of these selection guides guiding you to what antenna you might need in your specific case. Johansson Technology also has this in PDF form, and this document goes into quite a bit of detail how to choose, using their parts in this case, the correct chip antenna. Another way of doing this might be just go straight to your preferred distributor. This might be a Mouser, DigiKey, and so on, and then looking at then antennas. Now, they have quite a few antennas, of course, in stock. We have our typical connector type, where we have a cable going to connect onto our PCB, which was not what we're interested in, but they also, of course, stock ceramic chip antennas. Here we might narrow in on the frequency. We could select, for example, if you want to do Bluetooth or if you want to do GNSS and so on, and we can hone in onto various chip antennas. And immediately we can also see, for example, the price of these antennas. So in low quantities, typically maybe around 40 to 60 cents, and going down to about 10 to 20 cents in larger quantities and so on. Of course, we can get more expensive and cheaper ones. It depends on their performance. And ST nicely provides a couple of application notes and of course the datasheet for the microcontroller, which can help inform your choice of what antenna to interface this with. We might pick out, for example, the operation frequency band, what reflection coefficients we are allowed, the suggested minimum radiation efficiency, and so on. Additionally, there are other application notes, again, depending on what RF IC you're using from Texas Instruments or ST or Nordic and so on, and they will each have application notes and datasheets which tell you approximately the antenna parameters they might be working with or expecting, and if not, you should check out the evaluation kits these manufacturers provide. For example, for the STM32WB55 series, they have this nuclear board, and they might be using either a recommended antenna or have a chip antenna or a trace antenna directly on the PCB. And from that, you can get a ballpark value for the antenna parameters as a starting point. Again, this is very situation specific, again, as a good starting point. From the datasheet, you can also check out, for example, maximum output powers for transmission, and that's how you might choose, for example, your antenna power capability and so forth. So many different sources you have to pull together, and of course your application in itself to figure out what antenna might be right for you. If you're interested in learning more about these antenna parameters and what they mean, again, I'll leave some links in the description box below, talking about, for example, the bandwidth and frequency ranges, VSWR specs, antenna gains, directionality, and so on. And also application note AN058 by Texas Instruments gives quite a few more examples of different types of antennas and their properties and parameters. There are many books on this as well, talking about these various antenna parameters, which are important, of course, when you want to implement this in your own design. The actual antenna I went with was this by Abricon, which seemed to fit my needs fairly well. It's not too expensive, it's not too cheap, at about 50 cents in low quantities. You can see it has a certain gain, which of course you have to choose depending on your application, certain bandwidth, and a certain impedance seen at the feed point, and we'll see more of that later. Of course, we can go to the manufacturer website, then open the datasheet, and this will tell us far more information about this particular part. Of course, at the top of the datasheet, we can see the most important information first. We have our certain center frequency with the given bandwidth. We have the gains, voltage, standing wave ratio, the size, which of course can be very important for your specific design, and what mounting type it is. And we'll get into that when we come to the PCB design aspects, what power it can handle, and that it's already matched to 50 ohms, which can be very helpful. Scrolling down, we can see the dimensions, which is useful, of course, for the footprint, which we'll need later on as well. So if you want to create your own footprint, you would use the information as usual from the datasheet. Then what's important, and some chip manufacturers don't add this into their documentation, or it's not particularly easy to find, and that's why I typically skip those manufacturers. So it's great when you already have application test circuits and PCB layouts, how they recommend to mount the antenna. Again, we'll come back to this later when we come to the PCB design. They'll also tell you about matching, which we'll come to later as well, and give you some typical performance plots and radiation patterns, gain patterns of these particular antennas, depending on how they're mounted and so forth. And this definitely pays off because you need to choose this specifically for your application. A different antenna, let's go, for example, to this Texas Instruments application note, AN048, might explore a different chip antenna, just to show you an example as a comparison. Again, we'll see the dimensions of the chip antenna. As you can see, 7 by 3 by 2 millimeters. So very, very small devices. Again, we can see the frequency range, that is center frequency and bandwidth, radiation efficiencies. You can see this one has a different gain. You can see the type of polarization and so forth. And these are important parameters you need to pick out, again, depending on a specific application. You can see here, this particular antenna has a different mounting mechanism to the Abricon part we're actually going to be using in this video. So keep that in mind. Always check out the datasheet of how to actually mount this to your PCB and how to size the copper features around this. Before we move over to the schematic and PCB design, we need to talk about the matching network for these RF systems. In general, for example, if we have a transceiver and an antenna or an interconnect of RF systems, we might have a source with a certain source impedance, such as ZS, which is typically a complex value. And on the other side, for example, the antenna will be a load, and that will have its own characteristic impedance, its load impedance. So these are identified here by these generic impedance networks, so ZS and ZL. If we were just to connect ZS to ZL and these impedances aren't matched properly, we will get power loss, we will get reduction in efficiency, which will overall lead to worse RF performance. We might have to use slower data rates, we might reduce our bandwidth, we might offset our communication center frequency, and so on. So therefore, what we typically do is adding a matching network between our source and our load to make sure that, for example, our source sees the correct impedance and the load sees the correct impedance, that we get minimal power loss and maximum power transmission, very simply speaking. For further detail, I'll leave some more links in the description box below. For example, this blog post by Analog Devices, RF impedance matching, as well as allaboutcircuits.com, understanding impedance matching networks. And there's actually a whole series on this topic, as well as one of my favorite channels on YouTube, W2AEW, has many videos on, for example, designing impedance matching networks, basics of Smith charts, and things you need when you're looking at these types of RF systems. Again, links will be in the description box below. In our case, and this specific design for this RF dongle, I'm using this particular chip antenna, this AMCA31. Again, we have a center frequency of about 2.45 gigahertz and a bandwidth of over 90 megahertz, which when we're looking at the RF transceiver in this particular design seems pretty suitable, as we have a frequency range of about 2.4 to 2.48 gigahertz. What we did see earlier was that the datasheet stated right at the top that this is matched to 50 ohms, this particular antenna, which is typically the nominal characteristic impedance many RF systems are designed towards. However, this is slightly misleading. Scrolling down, for example, starting at page 3, we can see that there's some sections on matching circuit and reference values. So we can see we have the antenna on the left side, but we do have some components, for example, parallel, series, parallel, in between with recommended values. Scrolling down even further, we can then see this as a description of a physical layout, where on the right-hand side we have our PCB chip antenna, then a do-not-placed component, a series inductor of 3.9 nanohenries, and then a parallel capacitor of 1.5 picofarads, before we then have a trace that leads off to the rest of our system. The reason they have these components in is that the placement, layout, routing of this PCB chip antenna, the materials we choose, the proximity to other components will detune this PCB chip antenna. So instead of having a center frequency of, let's say, 2.45 gigahertz, this might be detuned quite severely depending on all the factors we just spoke about. We can see this in the datasheet if we scroll down even further, that before matching, we can see that this antenna, for the specific board they are measuring, they are actually detuned to about 2.8 gigahertz. However, after matching, after including all these components and tuning their values, we can see that center frequency at 0.2 is then actually 2.45 gigahertz with an impedance of about 50 ohms. So therefore, in pretty much all designs, I'd strongly suggest adding in a placeholder matching network. Now, even though they've given component values here, such as 1.5 picofarads and 3.9 nanohenries, again, this is very much system dependent, it's very much PCB dependent. So definitely put in these placeholder values, but you probably will have to tune these values on the real world PCB later on. If we then jump over to this specific example, the CC2500 RF transceiver datasheet, this datasheet actually has a section on RF matching and tuning as well. In particular, page 17 and section 7 application circuit, we can see we have requirements on a balun and RF matching. The balun in this case is specific to this IC. Effectively, it's converting balanced to unbalanced and vice versa. And there's more of a description in this section as well, but they give the components to match to a 50 ohm antenna. And they give specific external components to match this. So the actual network we see here, and this is the balun, so converting from balanced to unbalanced. So let's simply say differential to single-ended. We can see here we have the RFN pin, RFP pin, that has to go through this matching network. We then have this construction of C123, L122, and C124, which is the actual matching network to then convert to a 50 ohm impedance that is then seen by the antenna on the far right-hand side. The actual component values for 50 ohm antenna are then given below in this table. Now keep in mind, if you have a 50 ohm antenna, or if you're using, for example, some sort of coax connection, some sort of cable or connector, then those values are probably completely fine because your coax cable will typically be at 50 ohms, so you can start off with those values. However, we did see that for the PCB chip antenna we're using in this design, the actual PCB chip antenna impedance isn't exactly at 50 ohms, and it does require its own matching network. So there's a couple ways of going about this. You could either just copy over this matching network and then tune, for example, the values such as C123, L122, and C124 on the actual PCB design, or add in a second matching network afterwards. So copying this structure, this pi filter where we have a C, L, C, in addition, one after that, and then match that finally to the antenna. So with all of this in mind, jumping over to the schematic of the RF dongle and looking down the RF transceiver section, the CC2500, what I did was copy the structure from the datasheet of the CC2500, including the balun, which are these components now highlighted, and then the final RF matching network to match to whatever the characteristic impedance is of the antenna. In this specific case, I start off simply with the typical values for the RF balun given by the CC2500 datasheet, but then I did adjust C22, C23, and L3 to match to the particular impedance of the chip antenna that I'm using. Again, this will probably have to be tuned on the final design. So these are very ballpark values I just used using online calculators to give an approximate figure for this particular PCB chip antenna. But keep in mind, these do have to be tuned on the real world PCB, but they are a good starting point. As a different, maybe somewhat simpler example, I also have a design using an STM32WB55 microcontroller, which integrates a Bluetooth transceiver, and this also has an RF interface at this RF1 pin, pin 21, which has an impedance that isn't at 50 ohms, so it needs its own matching network, and it does need an external low-pass filter. But after that low-pass filter, we are at 50 ohms impedance, which then we want to connect to an antenna. But again, as we saw that our PCB chip antenna in this design isn't exactly at 50 ohms, it needs its own tuning and matching network. I've incorporated the matching network and the tuning network from the chip antenna datasheet, where we have that 3.9 nanohenry inductor, as well as the 1.5 picofarad capacitor, and the by default do not placed placeholder capacitor value. So this enables maximum flexibility on the final PCB then, because I can tune all sides of these matching networks, so the one towards the antenna and the one connected to the actual microcontroller pin. Just as another example, in the case of this ESP32 plus PCB antenna, we have very similar design, except of course we're using a PCB antenna. But what we have is in this case the ESP32, which is a Bluetooth Wi-Fi capable system on chip, LNA port, which is pin 1, which is effectively an RF port. We have a generic Pi matching network, which we can tune later. Then that simply hooks up to the antenna. So you will typically see very simple schematic structures like so. Again, taken from the hardware design guidelines from your specific manufacturer. Before we can move over to the PCB design, of course we have to create the footprint for our specific PCB chip antenna. This hopefully should be, of course, in the product dimensions and land drawings from the datasheet of your device. So if I scroll down a tiny bit on the left-hand side, we can see the datasheet, page 2 already lists the dimensions of the chip antenna itself, as well as suggested footprint. So all I've done is then taken over the dimensions, as you can see in the bottom, so F, H, G, and E, and moved them over to the design on the right-hand side. Keep in mind, all of these dimensions, as usual, will have some sort of tolerance. So for example, E, which is the pad width, has 1.6 plus minus 0.2, and this happens to be in millimeters. Of course, the pads themselves might influence the RF performance as well. So you should keep, of course, your manufacturing tolerances and constraints into account. For the pad width, you might go with 1.6 nominal, but I, in this case, went with a 1.8 wide pad, and G is 0.8 plus minus 0.2, so I went with a 1mm pad just to help out the assembly process and keep these tolerances in mind. With my pads, I like to use rounded corners, and this is not because of any RF property. It's actually to help the gasketing when they apply solder paste between the stencil and the copper openings or the copper lands, and that's why I typically round my corners on these pads, and we see typically a corner radius of about 25%. Unless it's a thermal or exposed pad, then I will only do about 5% as a rule of thumb. What's nice about this specific antenna, and I typically strongly suggest to do this as well, is to download the step file if available, or create your own, and then I import that into my ECAD tool. What's important also with these chip antennas is to mark the feed point location. You can see both on the left-hand side, the chip antenna itself on the top has this square marking, and also the step model has this square marking. And this is the feed point. And this is where our RF trace will then later come in when we come to the PCB design. The way I've marked this is simply a dot on the silkscreen, which lines up, so to speak, with the marking on the chip antenna itself. This is very important that you add that into the footprint. But that's all there is to the footprint design. Keep in mind the tolerances and indicate where the feed point is. With the footprint in place in the schematic, also our matching network, let's now finally move over to looking at the PCB design aspect. And this really depends on the specific chip antenna you've chosen. Each manufacturer should have their own recommendation of how to lay this out, how to do the grounding structures, what impedances you need, and so on. In the case of this Apricon chip antenna, if we scroll down to page 3 of the datasheet, we can see this chip antenna is this vertically aligned, so to speak, center mount antenna. If we zoom in a bit, we have our trace coming, let's say, from the RF pin of our microcontroller, going through our Pi matching network, and then feeding into the feed point of our chip antenna. At the point where this antenna starts, in this particular case, we have no ground around, so this is marked by this yellow area, and we have no ground underneath. In this case, they're using a 2-layer board here. So it's important that before we have our usual controlled impedance, then we hit the antenna and we have no ground, top, bottom, no copper, top or bottom, or any of the internal layers if we're using internal layers. Also keep in mind the orientation of the chip antenna, so this is not at a right angle, it is vertically aligned, so to speak. If we compare this again to a different ceramic chip antenna, we can see that we have a different mounting mechanism and a different attachment mechanism for our PCB for this other PCB chip antenna. And this is really important that you check out and you find a manufacturer that has good documentation and tells you exactly how to lay this out. Because any adjustment or deviation from the way this is laid out on the reference will of course impact the RF performance, regardless if we have to tune it later or not. This is also a reason why I chose this particular chip antenna. I wanted to be centrally aligned on my board. and the documentation was great. It included step files, the impedances required, and so on, and it was a very clear guide of how to implement this in my own design. So keeping this in mind, no ground around or underneath the chip antenna, that it's aligned vertically with our trace, let's move over to PCB design. Let's briefly remind ourselves of the schematic for this RF stick based on the CC2500 transceiver and the PCB chip antenna. We have our balanced connections at pins 12 and 13, our RF connections, then the balun consisting of these 6 inductors and capacitors, our RF antenna matching network with a CLC structure, this pi filter, and then of course our RF PCB chip antenna. Jumping over to the PCB, in general, with these fairly low frequency RF designs, so 2.4 GHz is a pretty common frequency these days, there's a couple things we of course have to pay attention to. I'd strongly suggest reading through the manufacturer design guides, notes, PCB design guides for layouts and routing, and that'll exist, for example, for the PCB chip antenna as we saw, and for example, the transceiver you're using. So make sure you consider the elements in those datasheets and application notes while you lay out your design, but of course there are some specific and general routing and layout guidelines for general RF designs. The first tip I'd like to give is to keep your trace lengths and your component sizes small relative to the maximum frequency of interest or apparent in your design. For us, this is about 2.4, 2.5 GHz. So to figure out the wavelength, all we do is take the speed of light, divide that by our frequency, so about 2.4 times 10 to the 9, so 2.4 gigahertz, and divide that by the square root of the effective dielectric constant. Because here we're routing as microstrip lines, our effective dielectric constant is about 3.3, so the square root of that. And that gives us then in millimeters about 68, 69 millimeters. So that's the wavelength of a 2.4 gigahertz wave traveling in the dielectric space of our PCB. So critical length, this is a very, very rough measure. That might be typically a 10th or 20th of the wavelength we've calculated. So let's say we go with the 10th, that gives us a critical length of about 6 to 7 millimeters. So as long as we can try and stay below that critical length, with component sizing, trace length, and so on, we don't really have to worry about impedance control, for example, of traces, because our component size is so much shorter than a typical wavelength in the design. So therefore, I typically like to get an estimate for what lengths I should stay under, but in general, I try to keep my length as short as I can anyway. So that's why if I go to 2D view here, and I, for example, measure my typical trace lengths very crudely, they are far below my critical length, which we just saw was about 6-7 millimeters. So here, first trace might be 1 millimeter-ish. Keep in mind, this doesn't take into consideration the actual internal package length, so the wire bonding, or however this IC is then bonded out, but it's a very rough measure anyway. Overall goal, what I'm trying to convey is try to keep your traces short. I haven't done any impedance control. This is just a 2-layer board with top layer signal, bottom layer ground. I do not have any impedance control, and if we keep our traces short, we don't really have to do this anyway. This is the reason also why I use these small package types. So this is an 0402 capacitor, for example. And if we measure its total length, it's about 1.6 millimeters. So far shorter than the wavelengths that we're dealing with in this design. So small package sizes, short traces is the overall goal typically with these RF designs, unless you have very specific requirements. So therefore I have very short connections, but from my CC2500 to my balun, I'm trying to package these components tightly, close together, but not of course too tight that I have DFM issues, assembly issues, and so on. So from my balun, these 6 components, then I have very short traces going into my matching network to my antenna. There are, of course, several ways I could have laid out my matching network. For the sake of size, I went with this vertically aligned configuration, but of course I could move my matching network around like so to give myself a bit more space, and I simply route through the components like so. But that gives me a longer overall distance. What I definitely don't want to do is have some sort of stub routing. So rather than having this component in series and in line, I don't want to move it, for example, like so, that I have to then increase my trace length unnecessarily. And I definitely don't want to have some routing like so, where I'm having these additional stubs before I then route where I actually need to go to. So try and keep this in mind. Try go for compact layouts where you can just route through components rather than having these branches and stubs. The general guidelines for RF apply. But now getting into the final interesting part, now we come to the PCB chip antenna, the actual focus of this video. So after all of our RF transceivers and matching networks, what do we do with our chip antenna? And there is no general guideline for this. You really have to look at the datasheet, what the manufacturer suggests. So going over to this specific chip antenna datasheet, going to page 3, looking at the PCB layout section. Here we can see there they have a 2-layer board as well. They have the antenna matching network placed like so, and this was an example we saw if we have the space available, and we have ground, top and bottom, this kind of coplanar microstrip arrangement with ground. Then once they hit the chip antenna, of course we have one pad, the bottom pad here with the dot, which is the feed point, and the top pad, which is just a mechanical support where we solder to. But effectively around the chip antenna area, so just when we hit the first pad, we have no ground. This is no ground on top. As we can see on the right hand side, there's no ground on bottom. But before that, we do have ground because we do need a return path for our microstrip lines in this case. Whereas the antenna should not have a ground underneath because we do want this to emit and not have the electromagnetic waves and fields couple to the ground plane below. These recommendations will of course vary depending on type of antenna you use and the manufacturer, the specific antenna and so on. But for this particular case, this looks like a center mount chip antenna and we don't want any ground around it and we want the feed structure something like so. Of course, depending on how you change the feed structure, where you place, for example, these inductors and capacitors of the matching network, you might detune the antenna. As we talked about before, you will have to tune the parameters of your matching networks in any case to get the optimum performance out of your chip antenna for your specific design. But going back to the design again, this is why we see here, if I go to 3D view, just before I hit the pad of this chip antenna, on the top and bottom layer where typically you would have ground, or ground fill on the left-hand side, I have removed the ground around the chip antenna. I don't have any components next to the chip antenna. I try to follow the manufacturer's guidelines as best as I can. Of course, you do see here, I do have my matching network fairly close up to the chip antenna, which might detune it a bit. So I could, of course, move the matching network around a tiny bit. But in any case, follow the manufacturer's guidelines. The way I removed ground around this is either you take your polygon pores on your PCB and you simply move them to be away from the chip antenna, or of course you can place a polygon pore cutout. So P in Altium Designer, for example, polygon pore cutout, and then I would just simply place a region that spans the chip antenna as it's suggested in the datasheet, and I would change that on the layer tab to multi-layer. Remember, you don't want ground on any single layer around this PCB chip antenna as per the datasheet recommendations. Other than that, at least very simplistically speaking, there's not terribly much else you need to take care of. Follow the manufacturer guidelines, keep your distances short, ensure you have matching networks in place so that you can tune this on the PCB. Because I've kept my distances short, my traces short, I do not need impedance control for this specific design. Lastly, you can also see I also have these stitching vias, so along the fence of these ground poles, close to my ground connections of my pads, because I then dig down, so to speak, to the bottom layer, which is my predominant ground polygon pore, my ground plane. And this is also very similar to what you see in the manufacturer guidelines here. With regards to stitching vias, please make sure to check out this article by Zach Peterson titled Everything You Need to Know About Stitching Vias, which goes into far more detail than we can in this video. Again, I'll leave many links in the description as we've discussed throughout this video, how to choose chip antennas depending on the application, benefits versus PCB antennas, or pros and cons versus other types of antennas, layout guidelines, and much, much more. But hopefully this video served as a basic introduction of adding chip antennas to your own designs. Thank you very much for watching this video. I hope it was useful and I hope it showed you how to incorporate chip antennas into your own designs, what to watch out for, when you might use them and when you might not use them. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest electronics, PCB design, DSP, and firmware videos. Thanks again, and I hope to see you in the next video. Bye-bye.